sleep and study. Don't forget to subscribe.
Good evening. Well, we have chosen a topic today that I would not say is particularly difficult, but that has changed surprisingly over the past few years. When we, well, Sarah a little later and I a little earlier, started studying astronomy, there was nothing but stars in space. And we knew that the cosmos was the stars, and they would tell us everything, and in fact there was nothing else to study. What seems important to us, planets, satellites, some meteorites, all this is such a small addition to the stellar population of the universe, well, like a pinch of salt, yes, here, no more than that. The situation has changed dramatically, and now we look at the population of our cosmos with horror. 2/3 or even 3/4 are not God. In general, no one knows what it is, under the conventional name of dark energy. This is something that has the property of anti-gravity, a fantastic thing, which, as it turns out, is realized in nature. Nobody will tell you anything about it, but it's there. We can feel it in the movement of galaxies. There's another quarter of the population of the universe, dark matter. We possess some knowledge regarding it. We comprehend that it aligns with the overarching principles of physics. Our understanding of dark energy is limited, while we are aware that dark matter is an unidentified elementary particle. Its mysterious nature stems from the fact that no lab on Earth has been able to detect it, yet it is perceivable in the cosmos. Scientists have been aware of these enigmatic particles for over 50 years. They, at the very least, exhibit the typical characteristics of gravity, for which we are thankful. However, we have yet to unveil their other properties and devise methods to capture and study them using laboratory instruments, although numerous physicists are actively engaged in this pursuit. But this does not annoy us much. We'll find a way to study them. Where are the stars? Well, it would seem that this is the population of space, although 5% of the universe in terms of energy and mass, but at least we know what it's made of. Protons, neutrons, electrons, something we experienced back in school as a medium familiar to scientists. But it turns out it's mostly gas, a medium almost invisible, hard to see. Even the coolest telescopes can't often capture it. It's very hot gas between galaxies. And there's only 5% of the universe. Of the universe, 5%, that's about 0.5% of the universe. You could forget about it and say that stars aren't worth studying at all because they're a tiny fraction. Nevertheless, when we look up at the sky, we see nothing but stars. And a telescope looking at the sky also sees nothing but stars. So whether we want to or not, we have to study the universe by looking at the stars, because there are practically no other sources of information, and they tell us a lot about the evolution of matter, about the evolution of ourselves, about the evolution of any pinch of salt in the guise of planets and biosphere on them. Well, in and of themselves, they're certainly curious from the point of view of physics to understand what's going on there. Looking at the sky with the naked eye, we see stars. Somebody may say, well, guys, you have modern equipment, a telescope, take it in your hands, and you will see something else in the universe. We take the telescope. We see more stars, but we don't see anything else but stars. And if we try really hard, we can see more stars. Even more stars. This is the world's biggest telescope showing us a picture like this. A tiny patch of starry sky. Photographed by a telescope just a little bit bigger than this audience, 8 meters in diameter. Well, that's about right, isn't it? The largest telescope has a mirror like this. Nothing but stars again. So you can't go anywhere to study the world on the basis of stars after all. And as it turns out, they were born in the past, were born in the not-so-distant past, are born today, and probably will be born in the universe for quite a long time. So first of all, we need to understand where they come from, how they are formed, from what environment these dense, beautiful, natural thermonuclear reactors are released that make the motion of the universe movement of matter in the world. This is, in fact, the only source of energy in the universe today. Well, almost the only one. It is starlight. We have stars of different generations in front of us, very old ones. over 10 billion years old since its creation. Our Sun, like many other stars, is a middle-aged star, often referred to as teenagers or youngsters. It is still in the process of being formed, like babies inside a protective cocoon of matter. In this discussion, I will touch upon the origins of stars and the fascinating process of their birth. The first half of our discussion will be dedicated to exploring the origins of stars, dissecting the intricate journey they undertake. We think we've understood so far. And the second part will be about how they evolve and what they turn into at the end of their lives. So there's a theoretical foundation. Physicists have long thought about how stars arise in nature. It was clear that since something gives off energy, it must eventually die. Well, heat. There's never an infinite amount of energy anywhere. So physicists realized that they had to figure out how to reproduce stellar matter. And quite a long time ago, they discovered, besides stars, also rarefied gas, and then we realized dust, small solid particles. Here's a dust cloud on the background of a hot gas cloud. At first, these, what our teachers referred to them as nebulae, as they possess a vague appearance, albeit often exhibiting a highly intricate structure. Initially, they failed to grab our attention. However, over time, we became convinced that they offered an explanation for the birth of stars. This ethereal matter must somehow transform into denser entities of colossal mass. But where does this matter emerge from? We witness it during every solar eclipse, in the form of a corona enfolding our sun. A mere glimpse at the solar corona allows one to comprehend that stars gradually lose a portion of their substance, which disperses. The coronae of individual stars intermingle, resulting in the phenomenon known as the stellar wind. Eventually, exceedingly rarefied matter accumulates in the interstellar expanse. When observing a visual representation, one cannot ascertain that the solar corona comprises rarefied gas. It possesses such tangibility that it appears as if one could simply cut through it with a knife. I dare claim that the ultra-high vacuum scientists have managed to create within their laboratories, referred to as the ultra-high vacuum, is dubbed so for the precise reason that it is highly improbable we will ever achieve the creation of an even more rarefied medium. Its density aligns with that of regions within the solar corona, with approximately 1 billion atoms packed into a cubic centimeter. Well, chemists and physicists realize it's a very rarefied environment, because we have billions of 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 atoms right now, right here in the air, right here in this cubic centimeter, and it's very difficult to pump a vessel down to like 1 billion atoms in a cubic centimeter. And for nature, it's a very tangible medium, and then as it leaves the neighborhood of the star, it becomes less and less dense, and it seems to disappear completely. Stars are formed from matter that is out of sight. When the sun loses its matter, it doesn't have a significant impact on its lifespan. Thus, this gas plays a role in the formation of stars. The sun will lose about 0.1% of its mass at the end of its life, an insignificant amount. But at the end of its life, the sun will start. This particular picture displays a violent eruption of matter resembling the behavior of this star. At one point in time, this star, a star that resembles our sun, is almost indistinguishable in mass. However, this star is older, with an age of around 10 billion years compared to our sun's 5 billion years. As it nears the end of its lifespan, it will leave behind a small core that contains approximately half of its original mass. The remaining half of the star's mass is rapidly lost within a span of about 10 million years, spewing it out intensely in all directions. We will talk about this more when we talk about the evolution of stars. We will talk about the cause of this phenomenon. Now, as you can see, half of the mass of the star returns back into space, back into the interstellar medium. These are what we call planetary nebulae. It's an unfortunate name, and it's been around since astronomers didn't have good telescopes. Looking at such an object from afar, in a poor telescope, you see some kind of blot in the sky, a foggy disk shaggy, and something Something it resembles the disk of a distant planet. In fact, this is a planetary nebula. It's not a planet-related environment. It's the last stages of a star's life. It looks very beautiful in the modern photographs that the Hubble Space Telescope gets, and we're very grateful for that. On the one hand, we're now admiring these pictures, but unfortunately, no, I'm kidding, not unfortunately, but fortunately for scientists, these planetary nebulae cannot yet be explained. Their shape is so complex that we can't understand how a spherical star, all ball stars, you look at them like a billiard ball, all the same on all sides. How do they organize in space around them in such a complex pattern? Today, you will also have the opportunity to observe images of planetary nebulae. These celestial phenomena exhibit incredibly intricate and complex shapes. It is perplexing to contemplate how a star, which initially appears as smooth as a billiard ball, can expel matter in specific directions, but not in others. Moreover, you will encounter numerous awe-inspiring forms of planetary nebulae. Fortunately for aspiring researchers, the physics behind these phenomena remains enigmatic, allowing for ample opportunity for investigation. This gas is gradually filling the space between the stars, and more of it is being added, not so harmlessly lost to the stars, I'd say. Here we have before us the well-known constellation of Orion, and by the way, here's the giant cluster of gas in which stars are forming before our eyes. And here's Alpha, Orion's brightest star, Betelgeuse. It's in the next 10 or so, maybe not, in the next 100,000 years or so. That's a blink of an eye. In the realm of astronomy, the event we refer to as stellar gas loss sheds light on the various ways stars can discharge gas. To form a colossal cluster of matter in which new stars can emerge, it's evident that the amount of gas expelled by the Sun and its celestial counterparts, similar to our very own Sun, would be insufficient. We require a more substantial influx, one that we observe during the demise of massive stars. So, take a moment to observe the substantial amount of gas that exists in the vast expanse between the stars. It appears as though there are no stars at all, doesn't it? However, this perception is achieved through a remarkable photography technique. By placing a light filter in front of the telescope, only the light emitted from the gas is accentuated, while the brightness from specific stars is deliberately diminished. In this way, the space seems to be solely saturated with gas. Through this process, we slowly begin to comprehend how this fiercely diffused medium can eventually condense into individual compact masses known as stars. You see, the majority of the gas emits a luminous glow owing to its high temperature and radiation akin to any other hot object. This tremendous heat is acquired as the gas is emitted from the innermost regions or surface of a star, and subsequently it gradually loses its intensity as it cools down. And as it cools, it starts to shrink. The thing is, there are no solid walls in space. There are no vessels in which the gas is enclosed. If some region of interstellar gas cooled down, the pressure in it decreased, and the surrounding hot, dense, high-pressure gas begins to compress it. It gets compressed and becomes more and more dense. Notice, right here. Dark, dense, seemingly invisible clouds. Here are the tiny ones here. Here are the tiny ones I think we can still show. Here we have a hot gas, and here we see a low visibility dark blob. It's actually much more massive than all the surrounding gas because it's already denser. Interstellar gas possesses a remarkable property that appears paradoxical to us. When we compress gas by using a hand pump to inflate a bicycle tire, almost everyone knows how to do it. This process, however, causes the pump to heat up in our hand. Why? We compress the gas and increase its internal energy, and it gets hotter. And interstellar gas, although it's also a gas, But under these conditions, the more you compress it, the faster it cools down. To cool down, the gas particles have to collide with each other, excite the electrons to higher levels, and they dump excess energy in the form of infrared radiation. So, by compressing the gas, you not only compact it, but also make it cool down a little bit. And once it cools down, it lowers its pressure, and it's even easier to compress further. It's called thermal instability in the interstellar medium. Studying interstellar gas presents a challenge because it is rarely heated to a temperature high enough to emit visible light. As it cools down, it becomes invisible to optical instruments. However, this does not mean it cannot be detected by other devices. The majority of interstellar gas is composed of hydrogen, which accounts for 90% of its composition. Additionally, helium makes up 10% of the gas, while other substances are present in very small quantities. Hydrogen, consisting of one proton and one electron, is the primary component of interstellar gas. Surprisingly, both the proton and electron have a magnetic moment resembling tiny magnets. This means they can be oriented in either a parallel or anti-parallel manner to each other. When they are oriented parallel, the energy of their interaction, two magnets, we know magnets repel when they have the same poles, is a little bit more. And when they're anti-parallel, the energy of their interaction is a little bit less. So the skipping of the electron, the spinning of the electron, and the turning of its magnetic axis from one side to the other causes the hydrogen atom. To release excess energy, it takes the form of an electromagnetic wave known as a radio wave. These waves have a length of 21 centimeters. This fortunate circumstance allows us to identify the presence of interstellar gas. The composition of this gas is primarily hydrogen, making up around 90% regardless of its temperature. However, it is more preferable for the gas to be cold and not ionized, existing in its atomic state. Radio telescopes have been crucial tools since the early 1950s for examining and detecting the interstellar medium. Nonetheless, there are other instruments available for this purpose. Before you, there are 4 complete star maps that provide an overview of the entire celestial sky. Similar to geographical maps that depict the Earth, these unfolded maps portray the vast expanse of the sky. Each of them is obtained in a certain range of radiation. Well, the optical telescope took us, photographed the whole sky, the band of the Milky Way. Black veins on it say that here cold gas on the background of hot gas can be seen. And this is exactly the same line, 21 centimeters long. It's got its frequency written on it, the hydrogen emission line. In our terminology, hydrogen that is cold is referred to as H1, and H2 is ionized hydrogen. And as you can see, along the band of the Milky Way is the largest cluster of cold interstellar gas. And this is hotter ionized hydrogen, and it too lies in the plane of the galaxy. It too is compressed to where gravity pushes it against the plane of the galaxy. And this is a carbon monoxide molecule, carbon monoxide. But this is a more complex substance, a molecule though not particularly complex. This is a very cold environment. These are the coldest regions of the interstellar medium, and they also lie in the plane of the Milky Way. In short, the medium from which, as we now know, stars are formed, it is pressed against the plane of the galaxy because gravity drives it there, to the center, to the potential pit, as a physicist would say, to the center of gravity of our stellar system. That's where it compacts. That's where it splits into separate fragments. Here's another wide-angle shot of the galaxy. The galaxy is flat, but in this wide-angle shot, it's so distorted across the sky. You can see it. And we can immediately see the dark veins, previously known as dust bags, act as barriers against the backdrop of stars. Hence, interstellar gas is not completely transparent as it absorbs light from distant sources. The gas itself does not possess significant light-absorbing properties. Consequently, the gas in this room does not impact our visual perception. However, if a dusty coal bag is disturbed, the resulting coal dust particles would obstruct our ability to see each other immediately. Even a mere few grams of dust would entirely absorb the light. This phenomenon is similar to what occurs in the interstellar medium. Within it, there exist solid particles which we commonly refer to as dust. These particles are minuscule in size. In terms of mass, they constitute approximately 1% of the interstellar medium. Nonetheless, they do not allow light to pass through them. As a result, these particles and the gas compact together towards the central plane of the galaxy, of the stars behind them. There are clouds where the interstellar dust is so densely packed that you can't see through them at all in the optical range. And of course, our predecessors, the astronomers of the 19th century, found it difficult to realize that it was here where nothing could be seen, where new generations of stars are born. If you can't see anything there, how can you even understand what's going on there? Today we have the technique of infrared telescopes, radio telescopes, for which even such dense clouds, translucent or completely transparent. We quietly study their internal structure and see that it is there that stars are born. Until 19th century, the process of star formation was not understood. Even in the middle of the 20th century, there were heated debates, especially in our country, about how stars are born. Maybe some of you remember the name of academician Victor Ambartsumian. No, you don't, do you? It's an Armenian. Well, by the way, after he graduated from the university, he worked briefly in St. Petersburg, in Leningrad. Yes, he graduated from Leningrad University. He is the head of the Armenian Astronomical School, the creator of the Bureaucratic Observatory, a very good mathematician, and he had his own original theory of the birth of stars from superdense matter of mysterious nature. We somehow resisted for a long time. We explained to him that nature makes stars in a different way, but he stood his ground, partly to highlight, so to speak, the PR of his observatory to create, but partly because we did not have enough arguments. Well, really, how to understand that in these cold clouds, in this one in the shape resembling a horse's head, it is so called the horse's head, this dark nebula, what is going on there? Little by little we figured it out. First, we realized that the interstellar medium is not homogeneous, that there are extremely large variations in temperature and density. The chemical composition is quite homogeneous. Astronomers today distinguish three characteristic types of interstellar medium. Cold. Since the temperature is low, molecules are able to form in this environment as they tend to dissociate easily at high temperatures. As a result, they are typically destroyed under such conditions. On the other hand, at low temperatures, these molecules are preserved. One example of this is hydrogen in the form of the H2 molecule, which exists in what scientists refer to as molecular clouds. Additionally, there exists a medium composed of individual atomic hydrogen. Physicists sometimes symbolize this as H0, while spectroscopists and chemists prefer this nomenclature. H1, alternatively, represents a medium consisting solely of hydrogen atoms. This medium is found at moderate temperatures, where the molecules are destroyed by heat and the atoms retain their individuality. They possess their own electrons and are neutral in nature. Finally, we come across a hot gas where H2 represents fully ionized hydrogen. This means that the electron and proton, the nucleus of the atom, exist independently of each other. In this scene, we can observe all three forms of hydrogen. It's quite cold at this location, and here, just off the screen, there is a scorching star that heats up a cold cloud with its rays. The intense heat prompts hot gas to rise, where it subsequently loses its molecular form and breaks down molecules. As the gas gradually approaches the star, it reaches a temperature of around 8 to 10,000 Kelvin. Electrons disengage from their atoms, and the medium becomes ionized. Consequently, all three types are present in this particular region. Which one of them, of these hydrogen types, is mostly responsible for star formation? The one where it's coldest. By the way, where it's coldest, it's also where the composition of the interstellar medium is most complex. Starting in the late 30s, first with optical telescopes and then with radio telescopes in different radiation bands, centimeter, millimeter, we began to discover molecules more complex than hydrogen. Hydrogen, you see, this is the very beginning of the list. These are the most widely represented molecules in the interstellar medium. Today that list is about 200 different molecules. The most complex ones have up to 13 atoms in them. Well, it doesn't seem like a thing, but among them are even amino acids. And biologists concerned about the search for life in the universe already say that the first steps to the evolution of life matter takes not even on the planets, but in the interstellar medium, forming, so to speak, the first protobiological molecules, some amino acids, there's glycine, some fullerenes, carbon complexes, and so on. It is in this relatively cold environment where molecules form that stars are born. Speaking of molecules, it's always a big challenge for nature. To create molecules from the same atoms. From different atoms, carbon and oxygen or hydrogen and oxygen, molecules are quite easily born. And this is very important for the further formation of stars. Molecules play a big role. But to put two atoms together, for example, of hydrogen, into a hydrogen molecule is very difficult for nature. Because what does it mean to combine? You can bring them together. The atoms fly around by chance. They get close, but they have to come together. That is, they have to shed their excess energy, and then they're going to bond, and then they'll bond together in some way. But how do you remove that energy if they're the same? Well, identical atoms, roughly speaking, don't know which one is destined. They're the same. They're arguing over which one of them is destined to dump the excess energy. When there are different atoms, it's always easier for them to solve this problem. So the role of the catalyst, that is, the organizer of the chemical reaction, is played by these very dust particles. They're few, but they're important, just like in an automobile. We have a little catalyst in the exhaust pipe, and it plays a very important role in converting bad gas into more decent gas. The hydrogen atom sticks to a speck of dust. I've drawn it round here. In fact, it is such an aggregate with needles, with an uneven surface, and begins to wander around it in search of the most convenient place where it could attach itself. Usually on some protrusions, where the electric potential is greater, it stops, sits, and waits. Waiting for what? For another atom to fly up and start wandering around the speck of dust, and eventually in the most favorable place. They'll meet and they'll unite and they'll come into contact. And then their energy of connection will be absorbed by the dust particle itself. It'll get a little bit hotter because of that, and it'll emit in the infrared. And they will be connected, and at the moment of connection they will even jump back, push off due to the energy released during their connection, and fly in free flight, leave this speck of dust, but already in the form of a molecule. That's very important because at low temperatures, atoms cannot radiate energy, but molecules can. When an electron within an atom moves from one energy level to another, there is a significant distance between the levels. If the atom is at a lower temperature, the electron remains in the lower level without jumping or emitting anything. Conversely, a molecule has numerous ways to alter its energy. It can undergo spinning or vibrating motions as its atoms move relative to each other, causing it to release excess energy in the form of very low energy quanta. Essentially, a molecule serves as an effective refrigerator within the interstellar medium. As molecules are formed within it, the cooling process continues, lowering the surrounding temperatures. The person who first demonstrated, with formulas in his hands, with physics in his hands, the process of star formation, it was the famous English astrophysicist James Jeans. He did a lot of things in physics, radiation, and gas, but he was the first to look at such a process. There is a gas medium, its atoms have First, gravity, and they want to be attracted to each other, and second, temperature, and they want to fly freely and fly away from each other. What's going to win? I'm going to show you literally 2 slides. If you don't like physics, don't pay attention to them, but for physicists it makes sense. In this scenario, a gas cloud faces 2 opposing forces, gravity and gas pressure. Gravity attempts to compress the cloud, while gas pressure aims to liquefy it and render it invisible. Both processes contend in a constant battle for dominance, subjecting the cloud to constant change. The one who works faster emerges as the winner. Either gravity will cause it to compress more quickly, or gas pressure will cause it to disperse more quickly. Therefore, we will create 2 formulas. The speed of sound is the speed of expansion, and the speed of gravitational contraction is related to attraction and collapse. Jeans wrote these 2 formulas and got 2 critical parameters: the size of the gas cloud and the mass of the gas cloud, and the symbol J is just related to his last name, James Jeans, which tell us that a big cloud, massive, will be defeated by gravity. A small cloud, not massive, will be defeated by gas pressure. It will scatter it. So there is a critical parameter, and for the interstellar medium, it's fractions of a light year. Of a light year, or a parsec, as we like to call it in astronomy size. And a fraction of a solar mass is the critical radius. Smaller clouds, they're not destined to be stars. They can't compress themselves with gravity. Big mass clouds have such strong gravity that they can compress themselves. But you see, it all depends on parameters, on temperature, and on the density of interstellar gas. What was known at the time of Jeans? This is the beginning of the 20th century, about 1922nd to 23rd year. Back in the time of Jeans, optical telescopes could only observe hot gas clouds. We were able to see brightly glowing nebulae like the Orion Nebula. However, we still wanted to understand more about their parameters. Fast forward to the 20th century. We discovered that these hot gas clouds had temperatures of around 10,000 Kelvin and very low density. When we applied the Jeans formula, we found that the critical mass of these gravitationally unstable clouds was gigantic, equivalent to hundreds of millions of solar masses. This was perplexing because stars of that magnitude were unseen and more akin to the size of galaxies. Something seemed off about Jeans's theory and how it explained the birth of stars. These monstrous masses were simply not observed in nature. Several years later, in the mid-50s, radio astronomy emerged, and we uncovered another portion of the interstellar medium known as the cool part. Here, the gas had temperatures in the range of 100 kelvins, considerably colder than before, and the density was higher. Even using Jeans' formula, we calculated masses around 20 solar masses. While we still didn't observe stars of such masses in nature, it was a significant improvement and indicated that these masses were becoming more plausible. A few more years elapsed, and we launched ultraviolet telescopes into space. They revealed the existence of an extremely hot interstellar medium, with temperatures approaching 1,000,000 Kelvin. Although it was extremely rarefied, this medium constituted a monstrous mass, equivalent to that of an entire galaxy. This finding didn't align with our previous observations either. Ultimately, it took until 75 years later, long after Jeans and his contemporaries had passed, for new astronomers, myself included as a graduate of the university at that time, to discover the coldest component of the interstellar gas, the molecular component. It, with its crazy low temperature, 10 Kelvin, it's minus 263 Celsius, the really terrible refrigerator, with its very high by the standards of cosmic density of 1,000 particles in a cubic centimeter, it is very much considered. Substitute that, and you get 4 solar masses. My goodness, it's a star. There they are, 5 solar masses, 2 solar masses, Sirius, Vega, they're in front of us. Well, finally, Jeans' formulae have explained the gas from which stars are born. It is the coldest, absolutely invisible for the optical telescope, but still felt by other instruments, cold molecular component of the interstellar medium. That is it, and is the birthplace for, the maternity home, rather, for the stars of new generations. It turns out that these molecular environments, or molecular clouds, are on an incredible scale. In our galaxy, there are roughly 5,000 immense clouds of cold gas referred to as giant molecular clouds. However, observe for yourself, each cloud has an average mass which approaches approximately 1 million times the mass of our Sun. In fact, within our solar system, no other objects of this magnitude can be found. Or almost none. There's 2 or 3 stellar ones, huh?
Is it like pillars of creation?
Those would be smaller in mass. The whole thing as a whole is it's about the same mass. The radius is huge, 20 pairs of seconds, a distance that's a lot of stars. Anyway, these are monsters we never knew existed before, and only millimeter wave radio telescopes have finally allowed us to detect them. These are the places where stars must be born. Now we understand how it happens. A cold big cloud, as it gradually cools, the pressure in it drops as it does so. It's compressed by the environment, by the pressure of the surrounding gas, by its own gravity. It thickens and cools more and more. But there's no such thing as complete homogeneity in nature. Some part of this cloud is colder and denser than the other, and separate dense areas stand out in it. The rate at which they shrink surpasses that of the surrounding matter due to their higher density, resulting in stronger gravity. As each fragment contained within the colossal cloud experiences rapid shrinkage under the influence of gravity, the gas within it gradually heats up during compression. Consequently, it endeavors to cool itself by emitting infrared light from its core. However, as it becomes increasingly opaque, the emission of infrared light becomes hindered, disrupting the cooling process and causing the fragment to instead heat up. The compression persists, causing the temperature within to rise. Soon enough, it reaches temperatures of 3 or 4 million degrees. That's the beginning of thermonuclear reactions. What we have in the hydrogen bomb happens in an instant. There it starts and continues for billions of years because the density is high, the temperature is millions of degrees, and thermonuclear reactions are going on. I'll tell you later which ones. And the surrounding outer part of the cloud is still cool, still rarefied, but it continues to fall there to the center under the action of gravity. So the very central region turns into a star. And the remnants of matter, so to speak, the construction debris left over from the formation of the star, it also has to go somewhere. And as we can see now, not just fantasize, but see, most of this matter goes into orbit around our newly formed star, possess a natural tendency to be drawn towards one another, resulting in them entering into orbital paths. The gravitational attraction between these entities compels young gas clouds to merge together and progressively acquire rotational momentum. The continual act of orbiting serves as the driving force behind any potential collisions that may occur amongst these celestial bodies. Has anyone ever collided with another vehicle on the road? You get bumped, you get spun around randomly, it's the same for them. But they speed up the process because remember figure skaters, she starts spinning slowly at first, but then she pulls her arms up, the moment of inertia decreases, and the angular velocity increases because the conservation of momentum causes the same phenomenon to occur in them as well. Initially, the peripheral matter compresses and slowly starts to spin. As time goes on, it unwinds more and more, eventually coming into orbit around the central, already young star. This matter becomes part of the cloud and gives birth to a gas disk around the star. It is within this disk that planets eventually form. A process no less mysterious than the birth of stars themselves, and still less clear to us than the birth of the stars themselves. But that's for another time. How did we manage to see everything? Fairly recently, hence the long-running debate, through the creation of a completely new kind of instrument. These instruments are called millimeter and submillimeter telescopes. Since we are discussing the observation of molecules, we need to be able to detect their radiation. And for this purpose, we use shortwave, specifically very shortwave, millimeter wave, wavelengths. Electronics mastered the art of generating and receiving signals only with the advent of satellite television. Various frequency bands from shortwave to satellite, FM, and even shorter radio and television bands came into existence. Eventually, Radio astronomers captured these signals using antennas and receivers, leading to the creation of numerous instruments. Among these, the most essential is a system of radio telescopes situated in Chile. Located in the northern part of the Andes, on the peak of Chajnantor, a plateau that stands 5 kilometers high, this system named ALMA, Atacama Large Millimeter, radio telescope or radio telescope system. It's a magnificent instrument. This is what it looks like in the nighttime moonlight. 60 plus antennas working in unison, looking at the same place in space and accumulating light. Not light, but radio waves. Well, it's hard to even say. It's something between light and radio waves. Very short wavelengths, such a peculiar range. But it's exactly the kind of thing you see molecules in interstellar light. And he showed us something that we'd only ever imagined before in our imaginations, but now we can see it for ourselves. A newborn star and the gas protoplanetary disk around it. Even these gaps perhaps indicate that the planets have already formed here and cleaned these corridors, cleaned them from dust, from molecules of gas, which shines now in this range, sorted on themselves, and have already cleared the corridors along their orbits. Before this instrument came along, it is a very expensive instrument. It was built with the collective money of most developed countries. We did not participate in it. Well, there's not much funny here, of course, but rather sad. It is a very expensive thing and very difficult to maintain. At an altitude of 5 kilometers, regular scientists are not able to work actively. It is serviced mainly by locals from Chile, from high mountain villages, who have been used to the thin air since childhood, while scientists work 1 kilometer lower, at the level of 4 kilometers, and conduct observations like this. In theory, we can consider this process sufficient. Nowadays, it can be simulated on computers. As the star shrinks, its center heats up, triggering a thermonuclear reaction. This leads to the formation of a cold protoplanetary disk around it. Although the disk continuously falls into the star, the overall process remains intact, but the radiation from the star itself prevents it from getting too close to it, heats up the gas, and tries to push it away. The hot gas wants to expand. But where does it want to push off to? Expand where? To the disk region, the equatorial region of the disk. It's dense here, you can't get through it, it's cold, it holds, and along the axis of rotation of the disk, it's almost empty space. And very often a young star forms two such fountains upwards and in the other one upwards. It has two tops, and it ejects the excess of this protoplanetary matter in the form of such diametrically opposed streams, jets. Well, and if there's anything left over that's not ejected, it all eventually coalesces into a small number of planets. Fantasy? Not at all. We are presently observing this process. Directly in front of us lies a frigid molecular cloud. Within it, a star has formed right around this location. Although we are able to detect it using radio waves, it remains unseen through an optical telescope. This star is encompassed by a protoplanetary disk, and it's got hot gas traveling in two directions. When it goes away from us, into the interior of the cloud, we can't see it, of course. It's dark, it's opaque, but here, this stream broke through the cloud shell, burst into free space, and we saw it. Here it is directed towards us, well, a little bit at an angle. Well, we see high speed, 100 kilometers per second, hits the rarefied gas. That's where the shock wave forms. Basically, the excess matter is shot out, and we realize that a new star has been born there, or there's another one, a star right here. One stream is coming towards us, the other stream is coming away from us into the interior of the cloud. You can't see the cloud, it's only visible in radio. That's where it disappears from our sight. And this one comes out. And even, look, you can see a spiral structure in it, like an auger. For engineers, it's what we use in a meat grinder to feed the meat. To the knife, it's an Archimedes screw. Apparently, it looks like that for a reason, because there are also magnetic fields that play some role in accelerating this gas. And they are so wrapped up in such a screw, and with their rotation, they help the gas to fly out, most likely. But this is already a theory. although the appearance of this object corresponds to this theory of magnetic acceleration of gas. It's very beautiful. Thanks again to the Hubble telescope for helping with this research. There are various regions close to us where numerous stars are currently forming. Interestingly, we have discovered that they prefer not to come into existence individually. We can observe a couple of small clouds where it appears that only a single star has formed. However, as a general rule, they are born together side by side. Although it may not be simultaneously, it happens at least once over a short period of time within a span of 10 to 20 million years. Some of this phenomenon can be seen in the Orion Nebula. Here, we have an image captured using both optical and infrared photography. In the optical view, we can observe 4 extremely hot and bright stars known as the Orion Trapezoid. These massive stars were born approximately 500,000 years ago and emit such intense light that they are visible through optical lenses. However, the rest of the objects would be invisible in the optics, but in the infrared they shine through and we can see them as newly formed clouds there in the interior, and this is where the star is not quite born yet. It's already formed, it's already become a heat source, but it's still shrinking. This is what's called a Kleiman-Low object. It's only visible in the infrared. Look at how it's actively spewing out the remnants, so to speak, of the gas that hasn't been incorporated into the structure of the star. They just accelerate to tremendous speed and fly like projectiles, penetrating the cloud, flying out into the rarefied interstellar gas. This shows that the young stars are trying to clear their construction site of excess matter, heating up the surrounding space, expanding the cloud, and in effect, destroying the maternity ward. The formation of their own interior was realized only after a considerable amount of time had passed. Look, here's another example. A massive star, massive stars are the most active, the hottest stars, has blown a bubble like this around itself. It's blown all the surrounding gas. It's emptied the space of gas. And it's basically empty space around it. And it keeps pushing its native cloud, which was once the beginning of this process. It's pushing it around and destroying it with its energy. There are some very massive stars. There's one in the constellation Carinae, Eta Carinae. It's so turbulent, it's hard to imagine where it got all that energy from in the 19th century. Has shown us it was at one time the brightest star in the sky. Now the matter it threw out has cooled down a bit. The star itself is no longer visible, but we see how actively apparently the remnants of the 19th century outbreak is scattering everything around it. There are hundreds of such birthing centers in our galaxy, but they're hard to study. We're sitting here. Our solar system resides within the galactic disk, which is saturated with dust and gas, making it opaque to our view. Consequently, observing the entire expanse of the galaxy is impossible as we ourselves are immersed in this dense matter. Luckily, neighboring galaxies, akin to maternity houses, provide a more convenient and comprehensive field of study. These galaxies are observable as unfolded images, akin to pictures, on a plane before us. Notably, we have spotted the vast gas cloud known as the Tarantula Nebula within one such neighboring galaxy, the Large Magellanic Cloud. Traditionally, the Magellan Expedition, Southern Hemisphere, first sailors discovered it in the sky. Now we call it the Magellanic Cloud. It's a neighboring small galaxy, but it's the largest known hotbed of new star formation. And right here, by the way, right here we see the most massive star ever discovered by astronomers in nature. It doesn't belong to our galaxy, it belongs to a neighboring galaxy, but its mass is more than 200 masses of our sun. To be honest, physics can't yet explain how such stars can sustain themselves and not collapse under the influence of their own energy released in them. Well, we'll explain it somehow. The important thing is that we've found it. What happens next? The newborn stars accelerate the gas around them. In the early stages of a developing stellar cluster, the gas surrounding them exerts pressure, causing the nearby cloud to compact and expel its contents into space. Eventually, the most massive stars in the group will reach the end of their lives and explode. However, our Sun follows a different path and will not experience such an explosion. Over the course of a few billion years, it will gradually shed some of its mass, forming a planetary nebula without any dramatic eruption. Consider, for instance, a star that is 10 to 15 times more massive than the Sun. It will progress through its aging process, will take 2 or 3 million years, which is extremely fast, and at the end of its life, and when it reaches the end of its life, it will release almost all of its matter into space in a sudden outburst. Although these events are rare, we do observe them. Around 1,000 years ago, in the year 1054, people on Earth witnessed the emergence of a new, brilliantly shining star in the Taurus constellation. Now we understand that it was a massive star that had exploded. Over the course of 1,000 years, the material it ejected formed an expanding nebula, expanding rapidly, containing approximately 12 times the mass of our own Sun. Therefore, it was a singular event of matter release, of a substance that has enormous energy. The gas is now traveling at somewhere around 2,000 kilometers per second. The kinetic energy is insanely large, and it will push around itself the rarefied, almost invisible here environment, long, actively destroy the cloud. So the young stars explode, they heat up around them, and you can see the cloud, and you can see the parent cloud gradually moving away, moving away, moving away, moving away, and this place is cleared. What's left in place of the huge gas cloud is a bunch of newborn stars. What is their fate? By the way, as now established, our Sun, like other stars, was born within a collective of newborn stars. It never existed in isolation and spent its early years in the company of other celestial entities. This fact is now firmly established. We can see that the stars are still in place. This is the Orion Nebula, which is a very original shot, where you can hardly see the stars, but you can see the gas. You can see that the cloud is already such a Barnard loop and completely left the star formation region. There was absolutely nothing there. Well, we see a gaseous medium, but this is the gas that is now flying towards us, here from the picture plane at us, and this gas that is flying perpendicularly there, and it seems denser because we are looking along the walls of this bubble. There it lies, a youthful cluster of stars. What shall become of it? Almost immediately, it became stripped of extra gas, retaining 90% of the mass which it originally held within the cloud. The cloud was huge, massive. A few percent of its matter turned into stars, and with their energy, the cloud was destroyed, and 90% of the mass was gone, and with it went the gravity of that cloud. The stars were moving around chaotically. Suddenly, they found themselves devoid of any binding force. Typically, the collective's internal gravity proves insufficient to maintain unity of this young collective. Here they are on their own, this young star cluster. And they've thrown a massive gas out, and they found themselves, most of them found themselves, moving too fast to stay in this place. Even the entities themselves have started to distance from where they were formed. We refer to this process as evaporation, because it closely resembles the evaporation of a liquid. Consider pouring a glass of water onto a windowsill, returning a week later to discover only half the glass remains, and returning another 2 weeks later to find the glass completely dry. Where do the particles vanish? Individually, they obtain sufficient velocity to escape from here and scatter within the confines of the room, never to return to the glass. The same behavior applies to stars. They interact and influence each other through their gravitational forces. The distribution of their velocities follows a specific pattern known as the Maxwell velocity distribution. Consequently, those that possess great speed can break free from this collective at the second cosmic speed. And now, as we observe computer calculations, we can witness how stars gradually migrate away from the region where they are formed. Among these stars, some move slower due to random factors and ultimately fall towards the center of this group. Moreover, there are instances where certain stars depart from the site of formation, while others with slower velocities gather to form a core where these slower moving celestial bodies concentrate. It is worth noting that the majority of young stars eventually venture away from the region where they were born, while the smaller ones congregate to create compact clusters under the influence of gravity. It is fascinating how you have already formed a cluster, isn't it? But about 2/3 of the stars that were originally in this region, they've already gone beyond the frame boundaries and were lost there. Well, they just started traveling around the galaxy on their own. So they're gone, oh well. Our sun also once left the collective in which it was born. But those that moved slowly sometimes form quite large star clusters. The smaller ones were destroyed faster, but the larger ones live for billions of years. And we see about 100 of them. We call them globular star clusters. And they have not lost their members since the youth of the galaxy. Well, not all members have left this collective and continue to live there together, moving chaotically. It's a very interesting object. My whole scientific career has been devoted to studying them because they are ancient. They remember in their structure of what was. And here's another globular cluster. It seems that they are right there, shoulder to shoulder, yes, stars, that they collided and stuck together. But this is the effect of our atmosphere. It blurs the image of each star. They seem to us such a teddy. So in fact, they almost never collide there and fly without collisions. Well, rarely. Sometimes they collide, of course, but very rarely. And so, like bees in a swarm, they travel without colliding with each other. Surprisingly, stars often exist in companionship, favoring a family dynamic by residing in pairs or sometimes even groups of 3, observing both double and triple celestial bodies. No commentary. But in the world of stars, it is a regular typical situation, because we have already found out that 2/3 of all stars observed by us are double stars, and about 1/4 of them are triple systems, and a small fraction of them are quadruple and even more complex. Our sun is an exception. The sun is a single star. The astronomer has always been concerned with explaining how double and triple star systems can form. Generally speaking, they can get reunions. This is the result of a computer experiment. We took 3 luminaries, 3-point masses, I've drawn them here as balls, and threw them into one region of space. They get closer, they don't collide, but they get so close that they actively attract each other. And look what happens. 3 random luminaries coming together in this area here. They interacted gravitationally so much that 2 of them, the first and the second, merged and lived together as a double star. And where did the energy of their connection go? And the third star here received a push at the expense of them, at the expense of attraction to this one, and left this area with great speed, carrying away the excess energy. And so out of the 3 stars, there's 1 single star and 2 double stars. Can that happen? It can. But you realize that for 2 stars to collide or come close together, there's still some possibility. But for a third star to accidentally fly into the same place at the same moment, the probability is so small that it could happen, but it's very rare. And it, as calculations show, is not able to explain the birth of all double stars. So what can we do? First, we have to take into account the more subtle effects of gravity. For example, if we envision the stars as inflexible and non-deformable entities, such as billiard balls, then when 2 celestial bodies come close to each other, the force of gravity causes them to turn their trajectory and with the same velocity went to infinity. Nothing happens, they did not connect. But we remember that the stars, despite their apparent solidity, are actually quite malleable. They are influenced by the forces of gravity and can deform due to mutual attraction. Similar to how the moon's gravitational pull affects Earth's oceans and creates tides, stars also induce tidal deformation in each other, causing their shapes to change. Through precise calculations, it is revealed that when a soft star approaches a larger, more solid one, it experiences significant stretching as it is drawn towards it. This stretching energy is a result of their gravitational attraction and is acquired from the star's motion. Instead of a trajectory that propels the star infinitely away, it ends up in an elliptical orbit due to this energy transfer and deformation. Comes back here again, deforms again, orbit narrows 2 or 3 revolutions, and it comes out. The star eventually settles into a circular orbit around the first star, and as a result, they become permanently interconnected in a binary system. This process holds a higher likelihood since 2 entities can encounter one another and allow for a third to ascend as well. But we're looking at a much more complex system. Here we see the famous star Castor. This is the brightest star in the constellation Gemini. Look what an interesting structure it has. 2 luminaries next to each other, 2 luminaries next to each other. This group and this group form a double relative to each other, and relative to them, another double system orbits in a wider orbit around them. 6 luminaries bound together in a single system. A chance encounter has been ruled out. Tides couldn't help either. How did nature realize such an object? And the idea came up from the other side. Mathematicians have long studied the deformations of bodies that have gravity and rotate and slowly shrink as they cool down. Researchers have explored abstract problems related to the compression of shapes within an ideal fluid. Although this abstraction separates from reality, it allows us to investigate the compression of a uniformly dense body at its initial stages. With time, as the body shrinks, its density increases. This change leads to the body gaining momentum due to its reduced size. The momentum causes the rotating body to flatten, ultimately transforming into a spheroid shape. The flattened body resembles a globe, with its flattening occurring along the axis of rotation. This transformation continues as the process progresses. Then the deformation gradually increases, stretching across the equator. And at some point, if nothing happens, it expands. Expands in compression, spins more strongly, and turns into a pancake of such a kind, a disk rapidly rotating, which still remains a single body. But at some point, it has the option to go down a different evolutionary line. If suddenly the central part of this substance bounced to the periphery, then instead of a pancake, we get a ring. A ring is also a single body. It's a long way from a double star. All right, let's see what's next. And it turns out that we had one more possibility of bifurcation, the separation of evolutionary curves into 2 directions. Here we have a slightly deformed ellipsoid could become not a compressed ellipsoid, but an elongated, as my students say, cucumberoid. And it could rotate around a short axis and extend in 2 directions, offering a slight perspective. The cucumber exhibits another characteristic, where it can stretch out and transform into a pencil while rotating. However, we are not interested in this specific aspect. Nevertheless, we notice another point of division. If some external force disturbs this shape slightly, the substance can disperse to the ends of the ellipsoid, elongating and creating 2 bulbils. At this juncture, we begin to perceive a hint of 2 separate objects within the dumbbell-shaped body, which gained recognition through the French mathematician Poincaré's description. As the connecting part becomes progressively thin, the matter will migrate towards the dumbbell's ends. Ultimately, it will split into 2 distinct objects. It is possible for the object to break into 2 separate fragments. The calculations indicate this possibility and suggest that such an event could lead to the formation of 2 distinct objects in the future, potentially even 2 separate stars. A 3-dimensional hydrodynamic calculation confirms this. What's more, it shows that it's not just binary, but more complex. This, then, is a calculation made approximately 15 years ago or so. Alan Boss described the phenomenon I'm about to explain. Over time, this concept has become more refined and detailed. We observe that the cloud has been gradually shrinking, and our focus lies within its central region. As the cloud shrinks, we reach a point where 2 fragments separate from each other. These fragments then split in half, resulting in the formation of a unique quadruple star system as promised by nature. As to where this matter will eventually go, the calculations were unable to provide a clear answer due to the excessive amount of computer time required. However, the primary substance divides into 4 distinct bulbils, giving rise to a system of 2 double structures. Both of these structures orbit a shared center of mass. Through the process of cloud compression, nature achieves this remarkable phenomenon known as fragmentation, gravitational instability, and subsequent disintegration into separate structures. We do observe such objects in space. This is such an emulation in TRID, an artist's picture. But in reality, we observe such stars, which are almost stars, and have not yet lost their mutual connection. The isthmus between them is preserved. It is unknown, most likely, they will break up and become 2 separate luminaries. But we see such objects. Of course, not as beautiful as in this picture of the artist, but by their properties, by the change in brightness of the mutual, we realize that this is the shape they have. Here is a standard model of the sun, and we see how the temperature from tens of millions, there from 15 million degrees in the center, gradually falls to the surface of the star and almost to 0. There are a few thousand degrees on the surface. It is almost. The pressure within a star decreases as the energy generation increases, causing the center of the star to be hotter due to thermonuclear reactions. As a result, the matter at the center of the star does not produce energy, but instead transfers it to the surface before being released into space. This widely accepted model of internal parameter distribution in stars has left astronomers with no doubts. However, the question remains, what keeps the star warm and maintains its internal temperature for billions of years while allowing it to continuously lose such a substantial amount of energy without undergoing any noticeable changes? It was not immediately clear what the source of this sustaining energy could be. In principle, what sources can be considered to explain this phenomenon? In the early 19th century, the concept of chemical reactions remained largely unknown. People generally believed that ordinary chemical reactions were responsible for the energy generated in stars. It was believed that matter inside a star, such as carbonaceous substances like coal, oil, or gas, would bind with oxygen, similar to how carbon dioxide is formed when fuel burns in a stove. This process would release energy. Scientists attempted to calculate how long the sun could shine solely based on chemical reactions as its energy source. For instance, we could measure the amount of energy released per kilogram of burnt fuel to estimate the duration of a star's functioning. We possess knowledge about the sun's mass, speed, and radiation power, which is unbelievably enormous, close to 1027 watts. By dividing this power by the energy released during a chemical reaction, we could determine the sun's potential lifespan. Unfortunately, it turns out that even with chemical reactions alone, the sun could only sustain its current level of brightness for several thousand years. A perfect match with the biblical idea of the age of our world. The early 19th century scientists were thoroughly impressed by its greatness, to the point that even the smallest coincidences made them joyful and confirmed the validity of the theory. However, as the mid-19th century rolled around, geologists began to question the idea of the Earth and the entire solar system being such a young age. They started calculating how rapidly sedimentary layers built up at the bottoms of lakes and seas, leading them to estimate that it would take hundreds of thousands, if not more, years for this to occur. This forced physicists to consider alternative ways to explain the continued existence of the sun. They discarded chemical reactions as a viable source of energy and turned to gravity. The idea was that when a stone falls from above and makes impact, it generates heat as the potential energy of the gravitational field converts into thermal energy. Additionally, a weight can be lifted on a pendulum clock, which then takes 24 hours to fall, generating energy throughout this process. The clock weight descends and releases its potential energy. The mass of the clock weight on the acceleration of free fall, on the height of the lift it descends, the energy is released, passes in the end into heat, in the gears, in the clock. A good source of energy is the sun. Massive body, large supply. We did the math, what could fall on the sun? We looked around, and in the solar system, there's a lot of dust in the space between the planets. There's so much of it that sometimes we can just see it. Especially in equatorial countries, after the sun goes below the horizon, we see such a faintly luminous but quite noticeable cone against the black sky. We call it the zodiacal light. It's along the ecliptic, along the zodiacal constellations. And we realize that these are dust particles that reflect the light of the sun. The sun's light is scattered on them. And we're a field disk that's in the space between the planets. Yeah, so dust is falling. Dust, meteorites, small bodies fall on the sun and warm it with their impact. Something seems to be missing here. The calculations indicate that there is an insufficient quantity of this substance. Then a commendable group of physicists, namely Meyer, took the initiative. Gengoltz and Kelvin performed the necessary calculations. They said, "Come on, what's on the outside? The sun itself is falling in on itself. As the sun's matter gravitates towards its own center, its upper layers begin to collapse onto the layers beneath it, causing the release of heat. If the sun continues to shrink and compress in its own gravity, the process of heat release will continue." And the calculation showed a simple form that such a source of energy will be enough not for 3,000, but for 30 million years. Once again, it's an interesting thought that scientists have discovered. Geologists have estimated that the Earth is millions, even tens of millions of years old. Meanwhile, astronomers have also substantiated the presence of an energy source that allows the sun to radiate for such extended periods of time. This discovery has put everyone's mind at ease, as it has helped elucidate these phenomena. It's worth mentioning that this theory has captivating implications. In the life cycle of any star, there are moments or entire eras in which gravity bestows its luminosity upon them. The birth of a star brings forth an epoch where it condenses from a nebula into a compact object, subjected to the relentless heat generated only by gravity for tens of millions of years. Similarly, the death of a star entails the core being stripped of other forms of energy, causing it to collapse into a highly dense state, relying on gravity as its primary source of energy. Nonetheless, additional energy sources are still required for the star's core existence during its longest evolutionary stages. Thus, a mere 30 million years falls short. When radioactivity was discovered, the chemical elements, uranium, plutonium, and so on, were found decaying at the end of the periodic table. At the very end of the 19th, beginning of the 20th century, radioactivity was discovered. It was used to measure the age of the Earth's rocks, and it turned out that the Earth was not millions, but billions of years old. So astronomy was out again. We had to stretch the evolution of the sun by billions of years. But the first idea is that uranium decays, so the sun is made of uranium. Something's decaying inside of it. Well, luckily, they didn't know that a lot of uranium is a good atomic bomb, and the sun would explode in a heartbeat if it had that much uranium in it. No, they needed another idea, and only in the end they paid attention not to the end of the Mendeleev table, not to heavy elements, but to the very beginning, and realized that not only decay, but also synthesis of matter from heavier elements, from hydrogen, helium, from helium to carbon, also provide energy release. These are called thermonuclear reactions, but for quite a long time physicists could not understand how they occur. The thing is, fusion involves bringing nuclei together, say a hydrogen-proton nucleus, in order for them to fuse and form a more complex nucleus. They just have to be brought closer together. And these are two protons, two positively electrically charged pieces of matter. They repel as homonymously charged particles. Try to bring them closer together, they repel. So to bring them closer together, they have to be accelerated to a high speed. This idea is realized when we accelerate them into each other in the particle gas pedal. But there's no gas pedal in the interior of the star. We make them here in the lab. In the interior of a star, the only process that can accelerate the particles so that they stick together properly, get close to each other, is temperature. The higher the temperature, the more active the motion. We've calculated what temperatures are needed for the fusion reactions of the nuclei of light atoms. Billions and billions of degrees. Those are the temperatures that would occur in a hydrogen bomb explosion. But there are no such temperatures in the interior of the sun. Calculations show that it doesn't exist. We're at an impasse. It seems that the only source of energy in stars is thermonuclear reactions, and the conditions in the interior of the star do not allow them to flow. And that's when a young Leningrad physicist, Georgy Gamow, solved the problem for the first time. He said, so we need to accelerate the proton so that it overcomes the potential barrier. That is, for it to approach, here is the second nucleus, for it to approach it, to pass over this potential barrier, and having approached so close, approaching the second proton, would be able, due to nuclear forces, which are not electrical but of a different type, to be bound with it forever into the nucleus of a more complex chemical element. Here it needs to accelerate in order to rise to this, as physicists say, potential barrier, to overcome the repulsive force. It doesn't have enough acceleration due to thermal motion to rise above this potential barrier. And Gamma, with the help of quantum mechanics, which had just been created at that time, showed that any small particle has a probability, without going over the barrier, to pass, as they say, to tunnel, as if to tunnel under the mountain, to pass this distance, only due to the fact that quantum mechanics says that any particle is smeared in space, that it exists simultaneously in several places, and it may immediately end up in the next place, no matter what wall separates it, no matter what wall separates the 2 points. It's the tunnel effect, so-called. It was discovered by a young man, less than 30 years old at the time, Georgy Gamow. Then he worked in the US and became a great physicist. By explaining this case, he showed that thermonuclear reactions can occur even at not very high temperatures. 5, 10 million degrees, it's not very high, and yet it happens. 2 protons flying, coming together, and they get so close that at some point they're going to come together into a stable system. In doing so, one of them undergoes a transformation. It transforms from a proton into a very similar particle, but without an electric charge, a neutron, and it throws its electric charge away in the form of a positron, the antiparticle of the electron. And then, having thrown away the positron and a small addition in the form of a neutrino particle, it forms 2 protons. This is such a connected system, a proton plus a neutron. The nuclear force between them is in effect, but there's no electrical repulsion, because the electrical charge has gone with the positron somewhere out there in the distance. What is this? It's still a nucleus of hydrogen, but now it's a heavy isotope of hydrogen, deuterium. Every now and then it meets another proton. There are lots of them flying around. And what happens? They combine, now that's easy, into the nucleus of a new chemical element. It says helium, 2 electric charges, plus a heavy particle with no charge. That's a helium-3 nucleus. They fly around until they meet the same helium-3 nucleus. And what happens to them? They merge. The extra particles throw the 2 protons out of their composition. They're too strongly repelled by the electric charges, and God forbid they fly off and form 2 protons, 2 neutrons. Physicists call it an alpha particle, but in fact it is a helium nucleus of the standard heavy isotope helium-4, but which we have in balloons. When we hold them on a string, they want to fly away from that very helium. And when they do, the extra protons are ejected with such force that they carry enormous energy and heat up the gas around them. That's the release of energy in thermonuclear reactions. The process of thermonuclear reactions is a highly complex scheme that unravels the inner workings of the sun. It begins with the merging of protons, forming a dihederium nucleus. This crucial step initiates almost all subsequent processes. Another proton is then added to create helium-3, which eventually transforms into helium-4. In this manner, 4 protons combine to form 1 helium nucleus, while also producing positrons and neutrinos as byproducts. Although there are some minor reactions, they do not significantly contribute to the main effect and are only considered in exact calculations. If the star is slightly more massive and hotter, there is potential for some fascinating thermonuclear reactions to take place. These reactions can be considered catalytic processes in the eyes of a chemist. meaning that the substance involved is not consumed but rather aids and enhances chemical reactions with other substances. For instance, if a star contains carbon, even in small amounts, it has the ability to bind 4 protons to itself. During the process, a helium nucleus is ejected while the carbon is transformed into nitrogen and then into heavy carbon and oxygen before returning to its original form known as carbon dosity, the standard carbon. At the same time, hydrogen is being transformed into helium through a reaction called the CNO cycle, which is an abbreviation for carbon-nitrogen-oxygen cycle. Although it occurs less frequently, this cycle is the primary source of energy release for massive stars. The chain reaction continues as neon is produced from the fusion of helium followed by the addition of carbon to obtain carbon and oxygen through the absorption of helium nuclei. This chain process leads to the expansion of the periodic table due to the occurrence of these thermonuclear reactions. However, with each subsequent step, the process becomes more complex and challenging. Take note of the electric repulsion between 2 protons due to their charge of 6 protons, which requires extremely high temperatures for this reaction to occur. The more massive the star, the hotter it is, and these reactions happen. Here are the stars with their masses in units of the Sun's mass, which we know today, from 50 to 1% approximately of the mass of our Sun. The parameters, the size of the star, the density of the center, the temperature at the center, and the radiation power, the luminosity of the star. These calculations are very accurate and we have no doubt about the numbers. We checked it all on astronomical observations. So today we have a pretty accurate picture of not only external parameters of stars, total luminosity, total size, total mass, but as you can see, we can guarantee what the temperature in the center is in millions of degrees. That's a colossal temperature right there, almost 40 million degrees in massive stars. The Sun is not very large, about 15 million degrees. The low-mass stars have very low temperatures. And this, in general, is a reliable result of astrophysical calculations. But how do you test it? Directly? How can we see those thermonuclear reactions that are going on deep inside the star, while we only indirectly see some effects of these reactions in the form of general radiation? How can this be tested in practice? Well, we have a clue. Look, when 2 protons merge, one of them turns into a neutron, a positively charged electron is ejected. And what else? This one doesn't have long to live. It immediately meets a negatively charged electron, annihilation, and they both disappear, become quanta of light. That's something we'll never see. It disappears into the depths of the star. And then there's this, is a neutrino particle. The neutrino interacts so weakly with any form of matter that, once born, it almost leaves the Sun at the speed of light, penetrates it at all without noticing the entire thickness of matter, and in a few seconds it leaves the surface of the Sun, goes into space, and then 8 minutes later it reaches the Earth. That is, 8 minutes ago, those neutrinos, which have arrived here now, were born in the core of the Sun. So, this presents an exceptional chance to investigate the activities occurring in the center of our celestial body. The only dilemma is determining how to capture and record them accurately. Our laboratory setup, our detector, they'll pass through it without noticing. Suffice it to say that right now, every single square centimeter of our body, including the tip of our nose, is penetrated by a mind-boggling influx of around 1 billion neutrinos emitted by the Sun per second. We don't notice it. Billions of neutrinos are passing through our body right now and going further. And it's evening now. Where's the Sun? Under the horizon. There on the other side of the Earth, they're passing through the globe, through us, and they go that way. And the device doesn't notice. So the device must be massive to intercept at least something from this stream. The first such device was made by an American physicist. even chemist experimenter Raymond Davis in 67th year. And so from the 68th year, he tried to register solar neutrinos. The instrument was built deep, 1.5 kilometers deep, in a shaft underground, so that this crust of the Earth would screen out everything from space except the neutrinos, which no layer of Earth can trap. He made a big tank, filled it with a substance in which there was a lot of carbon, and carbon atoms, the most sensitive to catching neutrinos, they sometimes turn into radioactive argon under the influence of neutrinos. That's what Davis was going to record. The experiment, well, I don't know. I just don't have the imagination to realize it. Almost 400 gallons of stinking liquid. And this is the liquid. The liquid that dry cleaners use to clean our stains, a very strong-smelling volatile liquid, tetrachloroethylene, or perchloroethane used to be called. In a gigantic tank, a week's time saw the birth of 12 argon atoms. Some of these atoms needed to be extracted from the vast volume for the purpose of measuring their quantity and determining the number of interacting neutrinos. The scientist bore the responsibility for this task, dedicating not just several years but even decades to conducting the experiment. Eventually, it was conclusively demonstrated that neutrinos do indeed originate from the sun. It seemed like a victory for astrophysics. It led to a significant burden within the field of astrophysics. In fact, one could even describe it as a crisis. Personally, I was witness to this development from the 1970s onward, when these findings began to surface through publication, because the neutrino flux measured was 3 times less than the theoretical prediction. It didn't add up. We were expecting the same number, and they came in 3 times less. Physicists told us, you don't know how the sun works, something else is going on there. We measured the neutrino flux, and we see that there are less neutrinos than astrophysics predicts. We timidly told the physicists, yes, we will try to clean something up, and we did. We made new models of the sun, where the core has a different chemical composition, that it is spinning, that there is a magnetic field. Somehow we wanted to slow down the reaction so that the theory would give less neutrinos from there. But, the physicist said timidly, maybe you don't quite understand what a neutrino is. We have a theory of elementary particles. The standard theory, all right, well, we'll try, we'll figure something out. And we did, we made other detectors. The thing is that neutrinos come in 3 different types. The birth of an electron or positron corresponds to an electron type neutrino. But there are also brothers of the electron. These are the mu meson and the tau. The mu particle and the tau particles are different types of neutrinos. These are the particles we usually focus on. In typical reactions, only electrons are created, and we anticipated them to come from the sun. We were not expecting any other types of neutrinos. The physicists assured us of this. Neutrinos have no rest mass, so they travel at the speed of light. This means that time effectively stops for them. As a result, when neutrinos travel at the speed of light, they do not have the opportunity to transform into different types of particles. Even though they are generated on the sun and detected on Earth, it is essentially the same moment in time for them. They simply do not have enough time to undergo metamorphosis. Therefore, we were only anticipating the presence of electron neutrinos. Well, gradually new detectors were made, and here in the neighborhood of 2,000 years in Canada was built a new detector of neutrinos, which had the ability to register not only electron, but also muon and also tau. And when all 3 types of neutrinos registered, it turned out that in the sum of their arrives from the sun, as much as the sun should be born electron. And that means that on the way from the sun to the Earth, they experience mutual transformations. And instead of the flow of electron flux, we have the same flux, but of 3 different colors, 3 different flavors, as physicists say. Well, it's conditional. They don't have flavors, of course. And then the astrophysicists got into a pose and said, well, we knew how the sun worked, but you were wrong about the neutrino. It has a rest mass, it travels slower than the speed of light, although not by much, almost the same but a little slower. which means it can transform on its way from the sun to the earth into other types. And now we look arrogantly at physicists and wait for them to create a new theory of elementary particles, which would take into account these transformations. It's a big victory for astrophysics in this intellectual debate. Well, all right, energy was born somewhere here, where it's hot and dense, and thermonuclear reactions are taking place. And the only way it can leave the star is from the surface into outer space. So how does it get from here to there? Well, we know three types of energy transfer. There's conduction. When you put a hot spoon in your tea, it gets hot on the handle. It's convection, where warm air rises up from a hot body, and it's transfer in the form of radiation, infrared light. Infrared radiation doesn't travel through the sun, and heat conduction is weak there. But convection, that's a good process. We heat the liquid from below, it boils and carries the heat to the top, and then it goes from the pot to somewhere in the kitchen. We're familiar with this process, and it happens in stars too. And it mixes the matter in the stars quite efficiently and carries the heat from the interior to the outside. It's helped, of course, by conduction in the form of quanta of light that break through the hot plasma. But convection is almost the main carrier of heat from the interior of the star to the outside. The star is boiling, constantly boiling, heated by its core. So we have already covered the basic elementary processes. Now let's delve into the life of stars. Firstly, stars are incredibly diverse. By analyzing the spectra of stars, which include different types, colors such as red, yellow, and blue, we can see that they are heated to varying temperatures on their surfaces. Some stars reach temperatures as high as tens of thousands of degrees, while others are in the thousands, and there are even some that are so cold that you could likely heat a piece of iron in your kitchen to 3,000 degrees, and it would emit a similar glow to a star, or at the very least, something close. We see that stars differ not only in their temperatures, but also in their masses, giving rise to various evolutionary sequences. When we observe a star, all we can perceive is its outward appearance. We are able to measure the amount of energy it radiates, the strength of its radiation, and the temperature found on its surface. All this information is right there before our eyes. So, let us continue to explore this fascinating world of stars and discover more about their intricate lives. We can construct a two-dimensional picture of the star's radiative power in units of the sun's radiative power, of course. The sun as a standard is always taken, the surface temperature. And it turns out that most stars in the universe are distributed along this diagonal. Powerful emitters are hot on the surface, and weakly powerful and quite cold on the surface. Well, that's not really surprising, is it? The hotter the surface, the more heat escapes from it. But it turns out that there are stars that are cold on the surface but powerful emitters. What does that mean? It means they have a big surface. So they're big in size. We call them giants. And then there are the opposite stars that are hot. You see, the surface temperature of white dwarfs and red giants can reach tens of thousands of degrees, making them very warm. However, despite their high temperatures, they emit minimal light and heat due to their small surface area. These types of stars, consisting of a small fraction of the total, are known as white dwarfs and red giants. The main sequence, which comprises around 90% of all stars in our galaxy, is commonly represented by the Hertzsprung-Russell diagram. This diagram was first developed in the early 20th century by two astrophysicists, Hertzsprung from Europe and Russell from America. It serves as a temperature and luminosity diagram highlighting the main sequence and its significance in understanding stellar evolution. While more specific classifications exist within the professional community, such as subgiants and supergiants, these details are not necessary for general astronomy courses. Hence, the main sequence of stars illustrated in the diagram caters to both professionals and enthusiasts, subgiants and supergiants. Deciphering the evolutionary analysis reveals how the fundamental attributes of our Sun evolve with time. At present, these attributes are considered as benchmarks, where the Sun is currently 4.5 billion years old, with a surface temperature, size, and radiation output serving as reference points. In the past, the sun was a little bit smaller in size, had a much smaller radiation output, and about the same surface temperature as it does today. And in the future, we can continue to do these calculations as long as the physics of the processes are clear. As the sun expands in its lifetime and increase the power of its radiation and cool down a little bit on the surface, not very much, but it will decrease its surface temperature by a factor of 1.5. But by increasing the surface area of the surface of light, the radiation power will increase. Fortunately, we're lucky with the sun, because if we were to model life, to simulate the life stars similar to the sun, but with a slightly different chemical composition, it turns out they would have a very different life. There are stars like this around us, luckily not our sun. Here's a star with very few heavy chemical elements. Astronomers call as heavy elements everything except hydrogen and helium, these two elements. Well, that's how we got hydrogen and helium, the main component, and we even call everything else metals. Although no carbon, oxygen are not metals, but everything else is metals. There's a fraction of a percent of them, and our sun has 2%. Like a pinch of salt and a micro pinch of salt. Is there a big difference between the two? It's a big difference, because these rare chemical elements act as a filter for the rapid passage of energy from the interior of the sun to the surface. They intercept the quanta and make them move more slowly to the sun's surface and stretch its life out over a longer period of time. The sun is still, here it is today, 4.5 billion years old, and it has another 4 or 5 billion years of quiet evolution ahead of it. Then there's a dramatic change, and if our sun had been born with less heavy elements, it would be ending its life today, maybe even yesterday. And man would not have had time to become man. So at the level of monkeys, our solar system evolution would have ended, and you and I would not have had enough time to evolve into Homo sapiens. But fortunately, the sun is slowly changing, and it has a few billion more years of quiet life in store. And then there will be violent change. Here's the evolutionary model of the sun again. In the center, the density builds up and reaches a very high value. Why? Because hydrogen is burned, helium is produced there instead, and it does not participate in thermonuclear reactions at those low temperatures, which are really in the sun's interior. And it, as a slag, is deposited there, compacted in the core of the sun. It becomes small, gravity on its surface is strong, and hydrogen there is heated to a high temperature and burns more and more intensively, but it burns up there. See, in the core of the sun, helium is accumulating and the amount of hydrogen is decreasing, and there is almost one inert helium core left in the core, incapable of thermonuclear combustion. It's compacted, and there's still hydrogen around it. And it continues to participate in thermonuclear reactions and becomes more and more intense, released as a heat source. And in the Hertzsprung-Russell diagram, the sun, during its, so to speak, final stage of evolution, will begin to increase its luminosity rapidly, and its size will increase 5 times, 20 times, 50 times. It starts to expand. Why? Well, I've come up with this analogy with a balloon. Look, we buy a balloon, but we used to buy them not inflated, but always in the form of this rubber band. It's opaque. We start to inflate it, and as it expands, it becomes more and more transparent. The same substance spreads out over a larger surface and becomes thinner and more transparent, when in the interior of the star, heat is released more and more actively, and the star has to dump the heat somehow, or it's just going to explode. Just explode. It expands, and as it expands, it becomes more and more transparent, and it's easier for radiation to escape. That's the reason why stars expand at the end of their life. The radiation power builds up, and the shell expands to release the excess of that radiation. This is the entire timeline of the sun's series of evolutionary changes, from its birth from a cloud of gas as it evolved, burning hydrogen in its interior. Today we're about halfway there. There will be an increase in the power of its radiation going forward, but so far it's not changing much yet. There's about 10% increase in the sun's radiative power over 1 billion years in our era. That's almost imperceptible. 1 billion years is only 10%. But then it starts to change very rapidly, and in about 100 million years the sun will swell into a huge red ball. We call it a red giant, a really big one. It will lose its shell. It's already inflating. It will simply leave the core. It will expand, and the core will remain, and it will cool the helium core, incapable of further thermonuclear reactions. In other stars, helium can continue the fusion process at high temperatures, and the sun is such that it will almost leave its helium intact. It's not a fantasy. We observe solar-type stars at different stages of evolution, and we see that there are giants, and as they age, they become more and more gigantic. The sun is like this today, and it will expand to a giant size. So let's compare in this illustration what the sun is like today and what it will be like in a few billion years. And how does that end for the planet? Well, of course, I'm showing you a robust version of evolution. When we do accurate calculations, we know how each star, depending on its initial mass, will travel along this Hertzsprung diagram. And we also know this: there are some stars are the not yet stars, those that are never destined to become a real star in their lifetime. Notice, this is our sun. This is one mass of the sun. These are the more and more massive stars. These are the less massive ones. But here's 10% of the sun's mass is where this picture ends. Why? Because if a star has an initial mass that's less than 10% of the solar mass, or 8% of the solar mass, it will never be able to start the fusion stage in its interior. The temperature there won't rise above 3 million degrees, not even hydrogen can burn, will not be able to participate in thermonuclear fusion. And it will, in its attempt to become a star, start to cool and cool and cool and forget that. And forget that it ever wanted to be a star. And a slightly more massive body will start a thermonuclear reaction in its interior and will remain in a stable state for billions of years, gradually burning hydrogen, turning it into helium. Here's a small difference in the initial mass, makes a big difference in the future body. These are the kind of non-stars we call brown dwarfs. They wanted to become a star, they wanted to light up, and then for billions of years, but they didn't have enough mass, and they are more likely to become planets, gradually cooling down, than real stars. So that's how we imagine the life of the sun today. The cloud of gas shrank, heated up, and having reached this point on the Hertzsprung-Russell diagram, it ignited a thermonuclear reactor in its interior and burned hydrogen for billions of years. When it burned it, it quickly began to expand, became red elegance, dropped the shell, and the core cooled down and turned into such a slag. First a white dwarf, then a cooling, very small compact object. During this fading already, in the last stages of evolution of the life of the star, for a while it becomes very restless. Its stationary state is no longer possible. At a specific area on the diagram, the star begins to pulsate. The change in behavior occurs as it crosses this particular region. We've always seen stars like this, but it took physicists a long time to understand it. Here in front of you is a series of photographs of a star cluster. This is the center, this is the periphery. See how some of the stars are flashing there? We've been tracking this for a long time. We called them variable brightness stars, but we couldn't understand the process. We felt like they were pulsing, but for what reason, I don't know. Their cause was first discovered not by an astronomer by profession, but by a radiophysicist, Sergei Zhivakin. He was working in Nizhny Novgorod, Russia. He was a specialist in oscillatory processes, and in radio engineering it is studied all the time. And he, interested in astronomy, in particular in variable stars, for the first time realized the physics of this process, that there is a valve mechanism that works there. It lets the radiation through, then holds it near the surface of the star. and the star changes its brightness on a regular basis. As the heart beats, as it shows itself on the cardiogram of hearts, so the star at a certain stage of evolution begins to pulsate. Well, you'd think we'd figured it out and forgotten, but it turns out that it's these pulsating stars. They're called Cepheids after the first one discovered, Delta, in the constellation Cepheus. They've been extremely useful, and they've helped us make a number of discoveries. Why? Because the period of their pulsation turned out to be related to their radiative power. This was first discovered by Henrietta Leavitt, an American astronomer, a deaf-mute woman, by the way. She was very active in the early 20th century, and she saw in her statistical observations that the brighter a star shines, the longer the pulsation period of its surface and brightness fluctuations. So when we see such a pulsating star in some distant galaxy, we can easily, in a few months of observation, find out what period it's pulsating with and find out the exact value of its radiation. Of its own radiation, the power of its radiation. And by comparing it with the apparent brightness of the star, we can tell how far away it is from us. It's a very hard problem for astronomy to measure the distance to distant objects. And here the Cepheid stars have proven to be the most reliable indicators of the distance to distant galaxies. So important, in fact, that they're the ones that allowed us to discover the dark energy in the universe, because they make it possible to measure the distance to galaxies. So the expansion rate of the universe is related to the distance to galaxies. It's a colossal discovery, essentially made by one lady. It's a remarkable story. She was housekeeper to the famous astronomer Pickering, and he managed a small group of men, as only men were involved in scientific work at the start of the century. However, when she noticed his work, she became intrigued, and he shared his knowledge with her. She started assisting him at home, not only in cleaning but also in performing calculations. He realized that she was more efficient than the men on his team, so he decided to disband it and instead hired 24 women for the same budget he had for 6 men. This team came to be known as Pickering's Harem, and together they achieved great accomplishments. No, only scientifically. And they made him discoveries that we still use today. Henrietta Leavitt, and this dependence, other spectral characteristics of stars to measure. They worked magnificently, and to this day, we still have half of the staff in our institute are women. That's what is atypical, generally speaking. For science, especially in the 19th century, in astronomy, women first showed themselves so actively. So, we're coming to the final stages of a star's life. Where do they end up? We've already figured it out. Those that are similar to our sun, having turned into red giants, inflated, gradually lose their shell. It continues to inflate and turns into such a cloud of gas leaving the star. This is how we imagined all planetary nebulae. Because the star is a ball and must lose gas from its surface very symmetrically in the form of a ball expanding in all directions. Yes, the Hubble telescope has shown us there are such stars, but it has shown us that there are also such planetary nebulae which surround themselves with some incredible pattern of lost gas, and there are more like this. We have already seen these are planetary, and there are more like this. So to understand how a balloon star can organize around itself such a complex pattern of material, of matter moving away from the surface, we're not yet able to understand. There is a set of separate shells and an incredible picture inside, and 2 jets that are ejected in diametric directions. How the star manages all this, by what forces it does this, gravity plus magnetic fields plus something else obscure, is beautiful and has yet to find an explanation. Well, in the end, okay, it sheds half of its mass, and the other half remains as the dying core of this star. Planetary nebulae are well studied. The nucleus heats up the surrounding gas. It glows, we will see, and the nucleus itself is a small object. What's left of the star, it's often comparable in size to our planet, sometimes smaller than even white dwarfs. They were discovered rather late. They're faintly luminous. You can hardly see them. They were discovered in the middle of the 19th century. And here was a young theorist, Indian. At that time, he was educated in India, worked for the first years there, Subramanian Chandrasekhar. He was young, I think 24 years old, a recent graduate of the University of Madras, for the first time made a calculation, and what is the fate of the white dwarf? And it turned out that the white dwarf cannot be very massive, that it maintains itself in equilibrium, gravity is compressing it, maintains itself in equilibrium by quantum mechanical forces. There is degenerate gas in it, and for a long time cannot resist gravity. And according to Chandrasekhar's calculations, it turned out that if we cold body, and the white dwarf is in fact cold, like a planet, build up its mass, then at first this planet-like body will be a body, then the type of white dwarf. But when it reaches a mass of about 1.5 solar masses, no white dwarf can keep itself in equilibrium and will have to shrink even more, formally to zero in size. He was censured for this. He was reviled. They didn't believe in his results. They scolded him. He first wanted to work in England, but they almost shamefully expelled him from there, saying that such a thing could not happen in nature. He went to the US and became a Nobel Prize winner in physics because his calculations were confirmed. And we now know that white dwarfs cannot be very massive, but can be no more than 1.5 times more massive than our sun. And we actually observe them. It's especially interesting when they're paired with another star. Here's one of the most well-studied stars, Omicron, the constellation of Cetus, and this is what we see in the telescope. This is what we see in another telescope into X-rays, and it's up to the artist to interpret what this system actually looks like. A normal, ordinary star, like the sun, and next to it, a white dwarf, and they revolve around a common center of mass, and the white dwarf, although small, but massive, and it pulls the matter from its neighbor, pulls the matter from its neighbor, and it gradually falls there, rotating for some time in the disk, because the orbital motion is preserved. The orbital motion is preserved, and so such double systems, where a small but massive white dwarf pulls the matter from its neighbor, we observe quite a lot today. And so these white dwarfs, referred to as they, become visible to us because they are small and unnoticeable. However, when they attract matter from their neighboring stars, an accretion disk forms and emits bright light due to the heat generated by the friction of its rapidly rotating layers. This gas emits various forms of radiation, including infrared, ultraviolet, and even X-rays. The capture of extra matter continues until a significant amount of pure hydrogen gas accumulates on the white dwarf. This accumulation process is a continuous cycle of matter falling onto the white dwarf that's already capable of a thermonuclear reaction. There was a white dwarf made of helium, which at this temperature does not catch fire, and it steals from its neighbor almost pure hydrogen, and hydrogen is just waiting to start turning into something new. And when it has accumulated there a lot, it actively begins on the surface of the white dwarf synthesis of hydrogen, helium synthesis from itself, and this in the form of an explosion occurs. You get a flash, and in the 16th, 17th centuries and up to now, we observe from time to time flashes of bright stars in the sky, and now we understand what it is. In 1901st year, we saw a flash in the sky, and today we take pictures. We see there is a double system, a white dwarf and a normal star next to it. And during thermonuclear explosion on the surface of the white dwarf, the ejected matter has already dispersed today. And it still continues to accumulate, gradually building up a critical mass of matter over the span of a few decades. Once again, in a few tens of years, it may ignite this fresh matter and unleash a powerful thermonuclear explosion upon its surface. However, that is not the only intriguing destiny that awaits. Consider the two white dwarfs that emerge from ordinary stars within a binary system. These could be either. As they orbit around a common center of mass, they gradually converge. The reason for this is that this dual mass system, are emitting gravitational waves. Now we register them on Earth. We know that this is a normal physical process. Through the loss of energy to gravitational radiation, the two bodies move closer together and finally merge, collide, and unite. They form a massive conglomerate that gradually loses equilibrium. Eventually, this conglomerate undergoes a rapid shrinking process, leading to intense heating and eventually a thermonuclear explosion. As a result, the entire system is obliterated entirely. And that's what we observe, that's what we call supernova star explosions. So the way we envision the life of a star today is this. A small star, like the Sun, at the end of its life loses matter in the form of a planetary nebula, turns into a white dwarf, but it can, if there are more white dwarfs near it, stick together with it and explode like a supernova. Either it will completely explode, nothing will remain of it, or a piece of it will shrink into a neutron star, an even denser and quite massive body. And then, the cores of stars that surpass the Sun in mass are typically already contained within the star. The nucleus is so massive that it transitions to the white dwarf phase and promptly transforms into a neutron star while inside the star. This process results in a substantial release of energy, causing the star to explosively shed its outer layer as a supernova flash. However, if the star is exceedingly massive, it continues compressing even in the neutron stage and eventually collapses into a black hole. These stellar explosions are usually observed in other galaxies rather than our own, due to their infrequent occurrence. In fact, the last observed explosion within our galaxy dates back to the 17th century. Although it wasn't us who noticed it, astronomers back then were able to observe such an event. And in developing galaxies, there are many of them, when you look at hundreds of galaxies, now in one, now in another, is happening. Here we have the Whirlpool galaxy in the Canes Venatici. Right there you can see there's a new star. That's a supernova explosion. It's kind of not a spectacular event, so to speak, but remember, there are hundreds of billions of stars. This is the glow of hundreds of billions of ordinary stars. And this, as it lights up, rivals them all, with all of them in terms of the power of radiation. So it's comparable to the glow of an entire galaxy containing hundreds of billions of stars. It unveils remarkably potent explosions, the most forceful ones ever witnessed in the universe. Can we anticipate and foresee these explosions happening in nearby stars? Yes, we can. Presently, our efforts are directed towards achieving just that. An example is Betelgeuse in Orion, which is on the brink of detonating as a supernova. In fact, it has already experienced a substantial burst. The transformation in its size is visibly evident as we observe it continuously. In contrast to most stars, Betelgeuse, along with another star, is studied not as mere points, but as bodies with distinct and defined surface geography. It has expanded in size to a colossal extent, indicating its imminent rumbling. The available models provide us with an understanding of the hotspots present on its surface. This is the boiling process of her matter that we can see. This is a model, of course. It's exactly what it looks like. Let's go back. Here's this picture of Betelgeuse with large hotspots in the atmosphere. And the model shows us how convective flows of boiling mass in its interior create such colossal temperature inhomogeneities on its surface. So we have a pretty accurate representation of the evolution of these stars. This is the model, and it's almost exactly the same as the actual image of the star. So keep an eye on the constellation Orion sometimes. You may be the first to witness a supernova explosion. We already know it's going to happen in the next 50 years. We can't be more precise because we can only see its surface, but the explosion is going to happen. In the interior, if we had the capability for very sensitive neutrino telescopes and detectors, we could closely monitor the Betelgeuse core and accurately predict when its explosion will occur, within mere hours. Unfortunately, we currently lack such advanced technology for neutrino detection. The explosion phenomenon in the core of a star is simulated theoretically using supercomputers, allowing us to visualize the various stages of this event. I will now present a movie that showcases a highly intricate three-dimensional model of the explosion. Watch closely as a thermonuclear reaction rapidly unfolds at the center. Although it occurs within a matter of seconds, we have slowed down the footage to display each phase in detail. Initially, the explosion appears slightly asymmetrical, causing the hotter matter to gravitate towards the section where it can easiest escape the star. This phenomenon resembles the rise of a mushroom cloud following an atomic bomb detonation, moving towards an area with lower atmospheric density. In a similar fashion, the explosion starts off-center, leading to the spillage of substance in that direction. However, due to the high temperatures, it remains trapped within the star. Eventually, you will observe the substance gathering on the opposite side of the star at a point antipodal to the original explosion. This asymmetrical supernova explosion exemplifies this recurrent pattern. As the simulation progresses, the substance begins to converge here, forming a heated cloud. Remarkably, such asymmetric ejections from supernovae are frequently observed. The beauty of this spectacle is undeniable. It is important to note that the calculation required months of extensive supercomputer processing in order to produce these impressive visualizations. We can do it here in a few minutes, but it is a very complicated thing because the mass of nuclear reactions and three-dimensional hydrodynamics, all of this had to be calculated. Carefully calculated. Here such calculations are made, and we see that a supernova star is a rather intricate tangle of thermonuclear explosions, and more or less resembles the result of real processes. Today, Orion looks like this. This is how we see it in the Earth's sky, and when Betelgeuse explodes, it'll look like this. It's not a big deal. It'll be a bright star, but it'll be about 10 times brighter than the full moon, so we won't have nights for a while. The radiation emitted during a supernova explosion is significantly stronger than that of a large solar flare. While it would be safe for us, the inhabitants of Earth near the planet's surface, astronauts in space, or satellites beyond Earth would experience a noticeable increase in radiation. They would have to find a way to survive the radiation shock. However, for us, Earth dwellers, it remains safe. The radiation power gradually intensifies over a few hours during the supernova explosion, then decreases over the course of several months. Eventually, we are no longer able to see anything, although there are occasional exceptions. 1,000 years ago, a supernova exploded in the constellation of Taurus, and today, this is the result of its explosion. And here we have a remnant, a nucleus. The very last episode in the life of the core of a star that's been compressed, which is a neutron star, that's where the neutron body sits. The discovery was made by a young PhD student at Cambridge University, Jocelyn Bell, for which her supervisor, Anthony Hewish, won the Nobel Prize. She didn't get it. To this day, the Nobel Committee is blamed for that, but she got hers. She became a famous scientist. But the Nobel Committee passed her by. She discovered these very nuclei of exploding massive stars, neutron stars. They were discovered by their strange periodic radio emission, like beacons, spinning rapidly and sending out radio pulses. We detect them, and we call them radio pulsars. More than 2,000 radio pulsars have already been detected, and they are neutron stars, that is, the most final stage in the evolution of massive stars. There are various unique ways that the life of a massive star can end. Besides white dwarfs, such as the fate of the Sun, and neutron stars, which are typically how massive stars conclude their life, there are also black holes. I'm sure you are quite familiar with black holes, as they are well known to everyone, including schoolboys. Black holes are even more massive than stars. Let me provide you with a complete overview of stellar evolution's culmination. Brown dwarfs do not transition into becoming a star at all. They bypass this phase entirely. Most stars eventually become white dwarfs, including the core of our Sun. Massive stars, on the other hand, can become neutron stars or even black holes. However, the most astronomically massive stars may erupt in such an extraordinary way that not even a black hole remains. Rather, a thermonuclear explosion disintegrates them in all directions. That's not to say this is the final picture. As long as it's a sketch of stellar evolution, there's still a lot of things we don't know, but that's probably where we should end the story. Thank you.
The question from the internet to the lecturer, which is not surprising. I would be grateful if you could ask it. I'm writing a science fiction story. As I understand it, it's a fantasy story. and I'm gathering various information for it. What would be the fate of a living being or planet Earth if, due to a tear in the fabric of reality or the occurrence of teleportation, a plausible scenario, a magnetar or neutron star were to appear in close vicinity? What possibilities lie ahead?
A magnetar is a neutron star with a very strong magnetic field. The others have strong fields too. Nothing will happen, as in, there will be no Earth.
The fantasy story will be over quickly. Of course it would.
Of course.
Without beginning.
Otherwise.
All right, what other planet besides Mars is still in prospect for human exploration?
There seem to be contenders for relocating us Earthlings to other planets in the future. Mars, of course, the most promising, but there are large satellites of the giant planets. These are Io, Europa, Ganymede, Callisto, Titan, a satellite of Saturn, on which the conditions as the sun will get hotter and the temperature comfort zone will move away from the sun, we will move from planet to planet in search of the most optimal conditions.
What about the atmosphere? It's not there anymore.
On Mars, it's almost gone today, yes, but there are polar caps there. They're cold today, frozen, but when it gets warmer, they'll evaporate and it'll be a little bit more favorable on Mars. I wouldn't say very favorable, but better than today. And then on the satellites of the giant planets, there is a huge amount of water, and at least we will have a warm ocean there. We are unlikely to find continents there, but in the end, we can also find oceans. Our ancestors are from there, and we've adapted. There's no other option.
What about the moon?
About the moon, it'll be the same as the Earth. When things get bad on Earth, they'll get worse on the moon. By the way, the latest calculations show that the sun, turning into a red giant, will first eat Mercury, just dive inside, then eat Venus. And we have long had doubts whether the expanding sun will reach the Earth's orbit. The latest calculations show that it will reach out and swallow the Earth. I mean, then the moon will dive into the sun's atmosphere.
Can a star cool down to the state of a mineral or a rock? And what would such a mineral or substance be called? How much could it weigh? And what can we say about gravity on such a star and a planet?
White dwarfs, which are formed from stars with a mass of around 1.5 to 2 solar masses, will primarily consist of carbon. Our sun, on the other hand, will form a white dwarf made of helium. In more massive stars, helium undergoes fusion and transforms into carbon, marking the culmination of thermonuclear reactions. Consequently, such stars will evolve into compact carbon-based bodies under the immense force of gravity. What happens when carbon is compressed?
Coal or diamond?
The calculations indicate that it could constitute a nearly solitary diamond crystal. The purpose of one that enormous is perplexing. Though unfathomable,
Totally.
envision a star composed entirely of diamond.
I'm pretty sure of it. Question for the lecturer. Will the Betelgeuse explosion hit the Earth or not?
It will, but not fatally. That is, our atmosphere will save us from this flow of radiation, just as it saves us from solar flares. But in orbit outside the Earth's atmosphere will be bad.
What is your understanding of the nature of dark matter?
None so far.
It's amazing.
No, there are hypotheses. These are elementary particles of a sort unknown to us. Physicists have a rough idea of their properties, and all these properties make them very difficult to find. Hundreds of laboratories around the world are building machines to catch the particles. I am teaching astronomy at Novosibirsk University for the 3rd year because I am invited every year in winter to give physics students a little bit of a boost in astronomy because there is a very large institute of nuclear research in Akademgorodok. They have built a facility to search for dark matter particles, but it is necessary to understand a little bit of the general, so to speak, background for young guys, what they are looking for, where these particles come from, because they have a real chance to catch them. And so, installations exist, but catching it remains elusive. There have been several reports of captures, but each time they have dissolved and been disproven. So far, it hasn't been caught.
Is there any evolution in large planets like gas planets?
All celestial bodies have an evolutionary process, and this is evident in the fact that the giant planets, specifically Jupiter, Saturn, and even Uranus, radiate more heat than they receive from the sun. This indicates that they possess a strong internal source of heat and energy. However, the exact processes occurring within these planets remain largely unknown to us. It is evident that some elements sink towards the center, while lighter ones rise to the surface. This differentiation in internal structure leads to the release of heat. Even without the presence of the sun, these planets would continue to undergo internal transformations and changes. Jupiter, for example, was different billions of years ago, emitting warmth and illuminating its satellites. Over time, it has cooled down, and it will continue to do so in the future. Nonetheless, planets have their own dynamic existence in full swing. We've got continents floating back and forth.
Well, and also when there are changes in the orbits of the planets, particularly when Jupiter migrates.
But it's not actually the planet changing, it's its motion in the solar system that's changing. Also interesting, of course, yes. And a little bit of atmosphere flies away.
Please tell us about the near future of neutrino telescopes. What neutrino telescopes do they plan to introduce, and what do they plan to study there?
The Sun remains the sole accessible source of neutrinos for research purposes. Additionally, in the rare event of a supernova explosion, a substantial flux of neutrinos is emitted within a few seconds, allowing for detection even from distant locations such as the far end of our galaxy. Neutrino telescopes can be found worldwide, with a particular mention of a large one located in the Caucasus. Multiple countries possess numerous such telescopes, which currently focus their attention on studying the Sun, while eagerly awaiting the occurrence of a supernova explosion. Up until now, the most recent explosion took place in 1987, during which only one neutrino telescope was operational. Yes, there was only one neutrino telescope, in the USSR in the Baksan Gorge, and he, I think, 3 or 4 neutrino particles caught, which of course no effect for physics. And now we are waiting for the nearest supernova explosion, because there are already dozens of neutrino detectors working in the world. They are being built, and a neutrino telescope is being built at the bottom of Lake Baikal, and at the bottom of the Mediterranean Sea, and at the bottom of the Pacific Ocean, and in the mountains of many countries deep in the mines, to shield the detector from foreign influences of other particles. And we're ready for what we're really looking forward to, Betelgeuse.
Is it possible that such mixing of the star's matter is caused by explosive processes exactly in the convective zone?
Oh, it's hard to talk about the convective zone there. It's a white dwarf, it's almost homogeneous. It has no energy sources, so there is no convection there. The red giant is what's swelled up on the periphery of the star, and the core is the white dwarf. It's the core that no longer has energy sources. That's where the thermonuclear explosion takes place. What here is a red giant is a shell that gradually flies away, becomes a planetary nebula, and goes away altogether. And the explosion develops in a small dense nucleus, which, well, if it is freed from the shell, we see it as a white dwarf, and if it is not freed, still lives inside this shell. We do not see it until the moment when it does not explode.
What about shell explosions?
In the case of shells, the conditions are not favorable. The density and temperature are both low. On the other hand, in a white dwarf star, which can be understood to some extent through quantum mechanics, degenerate matter is able to maintain equilibrium due to quantum mechanical effects. One intriguing property of degenerate matter is that as we heat it, the pressure within does not increase. In a typical explosion such as that of an ordinary bomb, the internal pressure causes the object to destroy itself until the explosion abruptly ends. However, in the case of a white dwarf undergoing thermonuclear reactions, as the temperature rises and the reaction rate accelerates, the pressure remains constant and the star does not immediately expand. It is only when all the matter within the star explodes that it suddenly expands, resulting in an explosion. This happens because for a period of time the star fails to recognize the fact that the process of thermonuclear fusion has already started to accelerate, and then it realizes too late that it should have expanded earlier.
You showed a graph that showed the temperature dependence of different layers of the sun, and there was a very sharp decline on it.
In the surface temperature.
Of the surface temperature, and for some reason it seems to go evenly, and then there's a sharp drop.
And that's because the star has expanded dramatically and its outer layers have cooled. They have already become so far from the core, where the energy is released, that while the heat reaches there, it already loses its shape, becomes infrared. The energy density liquefies, and there in the shell it is already quite cold quanta of such red infrared color. And we see it as the reddening, cooling shell of an expanding star.
Astrophysicists speculate at this point what might constitute a great attractor.
The Great Attractor is a discovery that was made when studying the motion of galaxies. We saw that the universe is not just homogeneous, i.e., galaxies do not fly away evenly in all directions relative to us, but there seems to be somewhere far away from our galaxy, a place that attracts them to itself a little bit more strongly than others, and there they fly away more slowly. There's a little more density of matter there than in our region of the universe. Well, it's only big in terms of size, and galaxies are expanding there, and they're expanding in our neighborhood. It's a little slower than our neighborhood. There, the initial density was a little more matter, and so the expansion process is not as active as right here, where our galaxy and its neighbors live. Well, it's not a big difference. Both there and here, galaxies will still fly apart. Today we know that they fly apart with acceleration, so the fate of both our galaxies is clear. It is not an attractor. It will not stop them. It will still let them go, and they will move away from each other, accelerating their movement. Dark energy will win here and there. Yes.
As the sun expands, is there a chance that our Earth will crawl away from the sun or fly farther away?
There's pressure, but it's very weak, and it's much stronger than other effects. For example, when the sun expands to the stage of red giant, and the surface of the sun is already close to the Earth's orbit, the Earth itself will begin to approach the sun due to the fact that there will be tidal disturbances on its surface under the influence of Earth's gravity. The Earth will, as if rocking the surface of the sun, transferring to it its energy of orbital motion and gradually spiral closer. The sun will approach the Earth's orbit, and the Earth will approach at this time to the surface of the sun in a spiral, gradually losing the energy of orbital motion. The solar wind has very little pressure on it and will not solve the problem. The Earth will dive into the atmosphere of the sun. It is already quite obvious.
I have a completely Philistine question here last year, if I am not mistaken, when gravitational waves were registered, among other things.
The year before last?
The question is, when fixing I have read a lot, is it possible to understand the source, that is the location of the source, where these gravitational waves are coming from? That is, roughly speaking, when I look at the sky, which way is the center of the universe?
Yeah, well, not the center of the universe, but the source of the gravitational waves. No, this has nothing to do with the Big Bang. The 5 pulses of gravitational waves that we have recorded in the past year and a half are all the result of the merging of black holes or neutron stars. The source of gravitational waves is the abrupt merger of 2 bodies. It is a complex phenomenon to comprehend. We have only detected these explosions in 4 cases using 2 gravitational wave detectors located in the United States. These detectors can pinpoint the origin of the gravitational waves within a 20-degree accuracy in the sky. The most recent registration of gravitational waves occurred in the fall of last year, on the 17th, when Italy's 3rd detector of gravitational waves came online. With the addition of this detector, we now have 3 points of observation, which allows for triangulation and makes our estimates of the direction more reliable. We directed optical telescopes towards the predicted direction and observed optical X-ray and gamma-ray flashes. This verified the existence of a true source where the stars had merged. The glow from the merger lasted a few hours, and we were able to capture and record it. It's worth noting that the actual detection of the flare was made possible by our robot telescopes, which react quickly to such events and are always operational. Among these instruments, our very own MSU University telescope was one of the first to capture the flare.
Do we currently have the simultaneous creation of matter and antimatter occurring right now?
You've seen positrons, positively charged electrons that are emitted when 2 protons merge. That's antimatter. The positron is the antiparticle of the electron, but its fate is just that. Having met any nearest electron, it will unite with it, and both of them will disappear, annihilate, and quanta of electromagnetic radiation will fly. That is, antimatter disappears instantly at the first encounter with ordinary matter with ordinary matter. Annihilation.
You said that stars are almost the only source of energy in the universe. What else is there?
Well, radioactive elements decay in the Earth's interior, which demonstrates the significant role of the sun. If the sun were to extinguish today, the consequences would be immediate, resulting in extreme coldness and sickness. However, underground dwellers would not sense the absence of the sun right away. Surprisingly, Professor Zavarzin's research revealed that the underground harbors a greater biomass of living microorganisms than the entire population of elephants, rhinos, and trees on the surface of the Earth combined. This means that if the sun were to vanish, life as we know it would cease to exist. It is worth noting that biology would still persist due to the heat emanating from the Earth's interior, a process unrelated to solar heat. Although it is true that every planet generates a certain amount of internal heat, the influence of sunlight is far more significant for Earth. However, this is not the case for Jupiter, as it receives a comparable amount of heat from within. In fact, Uranus receives more heat from its interior than from the distant sun, which only radiates some light towards it. Therefore, it is evident that many planets possess their own distinctive heat sources, all of which play a crucial role in sustaining their respective ecosystems.
Almost, in terms of the amount of energy.
In terms of quantity, some planets are more important than the sunlight that illuminates them. But for us, of course, the reverse is true.
What happens to the outer shell of matter when a star is born that turns it into a different substance?
Into a disk. It's very simple. As matter pulls toward the newborn star, it increases its rotational velocity. But this conservation of momentum leads to a figure skater. But the centrifugal force only balances the matter getting closer to the axis of rotation. But centrifugal force cannot balance along the axis of motion of the substance. Therefore, along the axis it continues to fall, and across the axis it is stopped from falling by the influence of centrifugal force. You get an oscillation.
My physics teacher, he's always questioning everything, especially when it comes to the concept of black holes. He says, what kind of black holes? Who has seen them?
A black hole is a massive object. However, its peculiar nature lies in the fact that its physical surface is positioned deep within the region where light becomes trapped by the strong gravitational pull of this celestial body. This boundary, known as the Schwarzschild sphere, marks a point of no return. Hence, once crossed, there is no chance of going back. In the case of matter falling onto a regular star, a white dwarf, or a neutron star, regardless of whether it approaches from a distance or not, it eventually strikes the surface, displaying visible impact. Yet, in the case of a black hole, anything entering from the outside quietly plunges inward, leaving no trace on its surface. There are objects that behave this way, in which falling matter is visible, but the surface shows no indication of impact, no luminous emissions, no disturbances. Consequently, based on these matching properties, we infer that these objects can be classified as black holes. While no direct observation has been made, their behavior aligns perfectly with our calculations. As a result, these entities are dubbed black holes.
From what I comprehend, the instrument named James Webb is expected to launch in the year 2018.
It's
Do you
better.
know the instruments it will carry and the direction
Angular?
it will focus on?
No. A global construction project has just been completed, resulting in a system of radio telescopes that will provide incredible image clarity. Spread across the globe, there are a total of 8 radio telescopes that can capture the surface of a black hole, including its event horizon. This achievement marks a significant leap forward in our understanding of such celestial phenomena. Well, literally this year it starts operating. We'll see it then.
So we'll wait a little bit.
No, well, we know several dozens of such objects with suspicion that they are black holes. Suspicions are almost 100%, but it is necessary to check them all the same, having looked at them right here in the same way.
In 2014 or 2016.
Years by machines such as Hitomi and Chandra have explored radioactive emission in the Perseus cluster.
I am considering X-rays as a possibility. Chandra is an X-ray satellite. Chandra is Chandrasekhar, the same one I showed you the portrait of today.
There was an unidentified, unrecorded, something unrecorded.
Thank you. Yes, that's a very interesting question because it's about the fact that we seem to have picked up some dark matter, this very dark matter. It's suspected that its particles occasionally merge with each other and emit electromagnetic quanta. And just the Chandra X-ray telescope, it's the American X-ray telescope in the world's largest X-ray telescope in orbit. It has detected just the very spectral line that physicists, one of the theories of dark matter, expects, predicts. Yes, yes. Yes? Yes, that's it. Well, it's still to be tested, of course, but in general, that would be great.
About the first slides, where we get this attitude, the dark energy, where basically it came from.
How do we know that? By direct measurement, dark matter manifests itself in gravity, and we, by studying the motion of distant stars, we can estimate the total mass of our galaxy because it attracts moving stars far out on the periphery of the galaxy. So we've measured the total mass of the galaxy, and then we looked at how much real matter there is in it in the form of stars, planets, interstellar gas. It turns out that somewhere 1/5 of the galaxy's mass is provided by stars and small planets, and 4/5. We can't see this stuff. That's why we called it dark matter, because it doesn't show itself in any way, but gravity does. There. Dark energy is more complicated. In 1955, we first discovered this fact. The expansion of the universe, that is, the scattering of galaxies in all directions, as it seemed to us before, must be slowing down. Just like when you pick up a rock and then it might even stop and then it might... There comes a point when an object might halt and move in the opposite direction. On the other hand, if it is thrown with speed, it will soar into space but eventually be pulled back by the Earth's gravitational force. As galaxies drift apart, they also exert a gravitational pull on one another. Scientists hope that our understanding of physics would explain this phenomenon, that the expansion of the universe, as well as the expansion of galaxies, would gradually decelerate. However, in the year 1995, it was observed that the expansion of the universe was actually accelerating. This led to the realization that there must be an unknown force opposing the mutual gravitational attraction between galaxies and pushing them apart instead. This force exists within the medium that resides between galaxies and possesses the intriguing property of anti-gravity or mutual repulsion. To calculate the average energy, we divide the speed of light by the square of the gravitational constant, thus determining the average density. In physics, energy and mass are essentially one and the same. As a result, it was deduced that this mysterious medium, known as dark energy, outweighs anything else in the universe, including both ordinary matter and dark matter. This is how scientists arrived at their calculations. Thank you all, and I'll see you next time.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.